Beyond the farthest reaches of our solar system, floating in the cosmic darkness between distant stars, lie worlds that could become humanity's new home. Right now, as you read these words, Earth-like planets orbit alien suns, harboring conditions so perfect for life that they might already be teeming with organisms we can't yet imagine. Today, we embark on the ultimate journey of discovery, exploring the most habitable exoplanets within our reach, and revealing which worlds could become the stepping stones to our species' survival among the stars. We'll venture to super-Earths, where gravity pulls 3 times stronger than home, yet liquid oceans stretch across continents larger than Asia. We'll discover planets locked in eternal twilight, where one side burns under perpetual daylight, while the other freezes in endless night, creating narrow bands of paradise between fire and ice. And we'll uncover worlds so Earth-like that standing on their surfaces might feel like visiting Earth's twin, separated by the vast emptiness of interstellar space. But here's what will shock you. The nearest potentially habitable world lies just over 4 light-years away, practically next door in cosmic terms. Using our fastest current spacecraft, the journey would take 70,000 years. Yet breakthrough technologies currently in development could slash that time to mere decades, making interstellar colonization possible within your lifetime. The question isn't whether we'll reach these worlds, but which one deserves to become humanity's first foothold beyond our solar system. Prepare yourselves. We begin our search in the Goldilocks zone, where temperatures are not too hot, not too cold, but just right for liquid water to flow across alien landscapes. 4.5 light-years from Earth, orbiting the closest star to our Sun, lies a world that has captured the imagination of every astronomer on the planet. Proxima Centauri b sits in the habitable zone of its red dwarf star, receiving just enough energy to maintain liquid water on its surface. This rocky planet, slightly larger than Earth, represents our nearest chance at finding a second home among the stars. But Proxima b harbours secrets that make it both tantalizing and terrifying. The planet is tidally locked, meaning the same side always faces its star, just like how the moon always shows the same face to Earth. Imagine a world where half the surface bakes under eternal noon, while the other half remains locked in perpetual midnight. Surface temperatures on the day side could reach 80 degrees Celsius, hot enough to boil away any standing water. Meanwhile, the night side plunges to minus 90 degrees Celsius, cold enough to freeze carbon dioxide from the atmosphere. Yet between these extremes lies a narrow twilight zone, a ring of perpetual sunset and sunrise where temperatures might be perfect for life. Picture standing on this boundary, watching the star Proxima Centauri hanging motionless on the horizon, painting the sky in endless shades of orange and red. Atmospheric circulation could transport heat from the blazing day side to the frozen night side, potentially creating a more moderate climate across much of the planet's surface. Recent computer models suggest that Proxima b might possess a substantial atmosphere thick enough to redistribute heat and maintain liquid water across significant portions of its surface. Water vapor, evaporating from the scorching day side, could condense into clouds that drift toward the night side, creating a global weather system unlike anything on Earth. These alien storms might rage for months, as atmospheric currents battle the extreme temperature gradients between day and night. The star itself presents both opportunities and challenges for potential life. Red dwarfs like Proxima Centauri burn their fuel so slowly they can shine for trillions of years, far longer than our sun's projected 10 billion-year lifespan. Any life that evolves on Proxima b would have virtually unlimited time to develop complexity and intelligence. But red dwarfs are also notorious for their violent mood swings, unleashing powerful stellar flares that can strip away planetary atmospheres and sterilize surface environments with deadly radiation. Proxima Centauri regularly fires flares containing hundreds of times more energy than the largest solar flares ever recorded from our Sun. These stellar tantrums bombard Proxima b with X-rays and ultraviolet radiation intense enough to break apart water molecules and gradually erode any atmosphere. Over millions of years, this stellar violence could transform a potentially habitable world into a barren, airless rock resembling Mars. However, recent observations have detected possible signs of water vapor in radio signals from the Proxima Centauri system, suggesting the planet might have retained at least some of its atmosphere despite the stellar bombardment. A thick atmosphere could actually provide protection from radiation, while maintaining surface pressures high enough for liquid water to exist. The planet's magnetic field, if it possesses one, could deflect much of the harmful radiation away from the surface. The journey to Proxima b represents the ultimate test of human ingenuity and determination. At 4.24 light-years away, the planet is incredibly close by astronomical standards, yet impossibly distant by human ones. Our fastest spacecraft, Voyager 1, would take 70,000 years to reach Proxima Centauri if it were headed in that direction. Even traveling at 10% the speed of light, a velocity that would require revolutionary breakthroughs in propulsion technology, the journey would still take over 40 years. But revolutionary propulsion concepts could make this journey possible within a human lifetime. Breakthrough Starshot, an ambitious project backed by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes launching thousands of tiny spacecraft equipped with light sails toward Proxima Centauri. These nanoprobes would be accelerated by powerful laser arrays to 20% light speed, reaching the system in just 20 years and beaming back the first close-up images of our nearest potentially habitable neighbour. Yet Proxima b represents just the beginning of our interstellar destination list. 12 light-years away, orbiting the star Tau Ceti, lies a planetary system that could harbour not one but potentially multiple habitable worlds. The Tau Ceti system has fascinated astronomers for decades because its star is remarkably similar to our Sun, only slightly smaller and cooler. Unlike the violent red dwarf hosting Proxima b, Tau Ceti shines with stable, steady light that has remained virtually unchanged for billions of years. This stellar stability creates ideal conditions for planetary atmospheres to develop and persist over the enormous timescales required for complex life to evolve. 5 confirmed planets orbit Tau Ceti, with at least 2 potentially residing in the habitable zone where liquid water could exist. Tau Ceti E and Tau Ceti F both receive amounts of stellar energy comparable to Venus and Mars respectively, placing them on the inner and outer edges of the system's Goldilocks zone. These worlds are super-Earths, containing between 4 and 6 times our planet's mass, which could dramatically affect their potential for habitability. The higher mass of super-Earths creates stronger gravitational fields that excel at retaining thick atmospheres over geological timescales. While Earth gradually loses atmospheric gases to space, super-Earths like those in the Tau Ceti system could maintain dense atmospheres for billions of years longer than smaller rocky planets. This atmospheric retention could create robust greenhouse effects that extend the habitable zone outward, allowing even the more distant planets to maintain liquid water on their surfaces. Tau Ceti orbits closer to its star, receiving about 60% more energy than Earth gets from the Sun. This extra heating could create a runaway greenhouse effect, similar to Venus, where surface temperatures soar to hundreds of degrees Celsius under crushing atmospheric pressure. However, computer models suggest that with the right atmospheric composition and cloud coverage, Tau Ceti could maintain temperate conditions suitable for liquid water oceans. The key lies in the planet's ability to reflect incoming starlight back into space. High-altitude clouds composed of water vapor or other reflective compounds could act like a planetary umbrella, shielding the surface from excessive heating. Ocean worlds often develop such cloud systems naturally as water evaporates from warm seas and condenses in the cooler upper atmosphere. The result could be a planet with a climate similar to Earth's tropics, warm and humid but not lethally hot. Tau Ceti F presents different challenges and opportunities. Located farther from its star, this super-Earth receives only 28% as much energy as Earth, placing it in the outer regions of the habitable zone, where Mars-like conditions might prevail. However, the planet's substantial mass could generate enough internal heat through radioactive decay to supplement the limited stellar energy. Geological processes like volcanism could release greenhouse gases that thicken the atmosphere and trap additional heat. The combination of stellar heating, internal geological heat, and a thick atmosphere could create surprisingly warm conditions on Tau Ceti F's surface. Scientists have proposed that super-Earths in the outer habitable zone might be ideal for life because they experience less stellar radiation while maintaining active geology that could support complex atmospheric chemistry for billions of years. But the Tau Ceti system harbors a dark secret that could doom any potential life. The system is absolutely infested with asteroids and comets, containing 10 times more debris than our solar system. This cosmic shooting gallery would subject any planets to constant bombardment by space rocks ranging from pebbles to mountain-sized killers. The impact rate could be so severe that complex life would face extinction events every few million years, preventing evolution from developing beyond simple microorganisms. However, this asteroid abundance could also provide crucial resources for future human colonists. The rocky debris contains vast quantities of metals, water, ice, and organic compounds that would be essential for building and sustaining an interstellar civilization. Mining operations in the Tau Ceti asteroid fields could provide raw materials for constructing orbital habitats, planetary bases, and even additional spacecraft for exploring other star systems. The journey to Tau Ceti would require even more advanced propulsion technology than reaching Proxima Centauri. At 12 light-years distance, even spacecraft traveling at 20% light speed would need 60 years to complete the voyage. This timeframe pushes beyond a single human lifetime, requiring either extremely long-lived crews, generation ships designed to support multiple generations, or advanced life extension technologies that could keep astronauts alive and healthy for the entire journey. Yet the potential rewards of reaching Tau Ceti could justify the extraordinary challenges. A sun-like star with multiple potentially habitable worlds represents the holy grail of interstellar exploration. Unlike the tidally locked planets orbiting red dwarfs, worlds around stars like Tau Ceti would experience day-night cycles similar to Earth, potentially supporting more familiar climate patterns and seasonal variations. 22 light-years from Earth, the star system Gliese 667c presents one of the most intriguing puzzles in exoplanet science. This red dwarf hosts at least 3 planets in its habitable zone, creating a cosmic neighborhood where multiple worlds could simultaneously support liquid water and potentially life. The system represents our best chance of finding not just one habitable planet, but an entire collection of life-bearing worlds orbiting a single star. Gliese 667cc, the most promising planet in the system, receives almost exactly the same amount of energy from its star as Earth receives from the Sun. This remarkable coincidence places the planet in the sweet spot where surface temperatures could mirror Earth's climate zones, from tropical equatorial regions to temperate polar areas. The planet's mass, roughly 4.5 times greater than Earth, suggests a substantial rocky world with strong enough gravity to retain a thick, protective atmosphere. The higher gravity on Gliese 667cc would create a fundamentally different experience for any potential inhabitants. Humans weighing 150 pounds on Earth would feel like they weigh 240 pounds on this super-Earth, making every movement require significantly more effort. However, this intense gravity could provide crucial benefits for long-term habitability by preventing atmospheric escape and maintaining stable surface pressures over geological timescales. Computer models suggest that Gliese 667cc could possess vast oceans covering most of its surface, interrupted by island chains and perhaps smaller continental masses. The combination of higher gravity and extensive water coverage could create unique weather patterns dominated by massive storm systems that dwarf Earth's hurricanes. These superstorms might persist for weeks or months, redistributing heat and moisture across the planet's surface in ways that could support diverse ecosystems. The planet's position in a triple star system adds layers of complexity to its potential climate. Gliese 667c is part of a gravitational dance with two other stars, Gliese 667 Ampere and 667b, located roughly 20 astronomical units away. While these distant stellar companions don't significantly heat the planets around Gliese 667c, they create spectacular celestial displays that would dominate the alien night sky. Observers on Gliese 667cc would witness not one but three suns of different colors and brightness levels. The primary star, Gliese 667c, would appear as a large orange-red disk, providing most of the planet's heat and light. The two companion stars would shine as brilliant points of light, one orange and one yellow, bright enough to cast shadows and provide significant illumination during the planet's night cycle. This multiple star configuration could have profound effects on the evolution of any life forms that might develop on Gliese 667cc. The complex gravitational interactions between the three stars create slight variations in the planet's orbit over thousands of years, potentially driving climate cycles that could accelerate evolutionary adaptation. Life forms would need to adapt to changing seasonal patterns and varying amounts of stellar radiation, potentially leading to more diverse and resilient ecosystems than those found on single-star planets. The other potentially habitable worlds in the Gliese 667c system, planets D and F, orbit at different distances from their star, creating a variety of climate zones within a single planetary system. This cosmic archipelago could represent the ultimate destination for interstellar colonization, offering multiple worlds with different environmental conditions to support various types of human settlements and industrial activities. Gliese 667 Candela orbits closer to the star, receiving about 90% of Earth's solar energy and potentially supporting warmer, more Venus-like conditions. If the planet possesses a thick atmosphere, it could maintain liquid water oceans under dense cloud cover, creating a greenhouse world where surface temperatures remain stable despite the reduced stellar heating. Such conditions might be ideal for certain types of agriculture or industrial processes that benefit from consistent warm temperatures. Gliese 667 CF occupies the outer edge of the habitable zone, receiving only 39% of Earth's solar energy. This distant world might resemble a warmer version of Mars, with thin atmospheres and seasonal polar ice caps that advance and retreat as the planet follows its elliptical orbit. The lower energy input could create more stable climate conditions with less extreme weather, potentially offering safer environments for initial human settlements. The journey to the Gliese 667 system would represent humanity's most ambitious interstellar expedition. At 22 light-years away, even the most optimistic propulsion technologies would require journey times measured in multiple human generations. Breakthrough propulsion concepts like fusion rockets or antimatter engines could potentially reduce travel times to 100 to 200 years, still requiring massive generation ships capable of supporting self-sufficient human communities for centuries. However, the presence of multiple habitable worlds makes Gliese 667c an attractive target for humanity's first serious attempt at interstellar colonization. Rather than betting everything on a single planet like Proxima b or Tau Ceti e, colonists bound for Gliese 667c could choose from multiple worlds, each offering different advantages and backup options if initial settlement attempts face unexpected challenges. The system's stability and the presence of a sun-like stellar environment make it perhaps our best chance of establishing a truly permanent human presence beyond our solar system. The search for humanity's next home extends beyond individual planets to entire systems that could support multiple colonies, and nowhere is this more evident than in the TRAPPIST-1 system. Located 40 light-years away in the constellation Aquarius, this remarkable star system hosts 7 Earth-sized planets packed into an area smaller than the orbit of Mercury. 3 of these worlds sit squarely in the habitable zone, creating the densest collection of potentially life-bearing planets ever discovered. TRAPPIST-1 itself is an ultra-cool dwarf star, even smaller and dimmer than Proxima Centauri. This cosmic ember burns so slowly it will continue shining for over 1 trillion years, providing eons of stable energy for any life that might evolve on its planets. The star's modest size means its habitable zone lies incredibly close, with the outermost potentially habitable planet completing its orbit in just 18 Earth days. This compact configuration creates a gravitational symphony unlike anything in our solar system. The 7 planets are locked in a complex chain of orbital resonances, where their gravitational influences create precise mathematical relationships between their orbital periods. For every 8 orbits of the innermost planet, the second planet completes exactly 5 orbits, the third completes 3, and so on, in a cosmic clockwork that has remained stable for millions of years. TRAPPIST-1e emerges as the crown jewel of this planetary collection. Receiving roughly the same amount of energy as Earth gets from our Sun, this world likely experiences moderate temperatures that could support vast liquid water oceans. Recent analysis of the planet's density suggests it contains less rock and more water than Earth, potentially making it an ocean world with water covering its entire surface to depths of hundreds of kilometers. Standing on TRAPPIST-1, E would offer views that no human has ever experienced. The other planets in the system would appear as large, brilliant disks hanging in the sky, some appearing twice the size of our moon. The closest neighboring worlds would show surface features visible to the naked eye, allowing observers to watch weather systems swirl across alien continents and witness the dance of other moons around their companion planets. The planet's likely tidal locking creates the familiar pattern of eternal day and night sides, but the presence of a deep global ocean could dramatically alter this world's climate. Ocean currents would transport heat from the perpetually sunlit hemisphere to the dark side, potentially maintaining liquid water across the entire planetary surface. Massive storms would rage along the terminator line, where day meets night, creating a belt of perpetual tempests that could span continents. TRAPPIST, 1 farad and 1 gram occupy the outer edges of the habitable zone, receiving 38% and 25% of Earth's solar energy respectively. These cooler worlds might resemble icy versions of Earth, with frozen surfaces hiding liquid oceans beneath miles of ice. Like Jupiter's moon Europa, these planets could harbour vast subsurface seas, warmed by tidal heating from their complex gravitational interactions with neighbouring worlds. The gravitational tugging between the tightly packed planets creates internal friction that generates heat through tidal flexing. This process could keep subsurface oceans liquid for billions of years, even on worlds that appear frozen from space. The hidden seas beneath TRAPPIST-1 farad and 1 gram might contain more liquid water than all of Earth's oceans combined, creating environments where life could flourish in eternal darkness, fed by chemical energy from the planet's rocky cores. But the TRAPPIST-1 system presents unique challenges that don't exist around larger stars. The planets orbit so close to their dim star that they're bathed in intense stellar radiation, particularly high-energy X-rays and ultraviolet light that could strip away atmospheres over geological time. The star's youth means it likely experienced periods of even more violent activity in its past, potentially sterilizing any early attempts at atmospheric development. Recent observations using the James Webb Space Telescope have begun probing the atmospheres of TRAPPIST-1's planets, searching for the water vapor, carbon dioxide, and other gases that would indicate substantial atmospheric retention. Early results suggest that at least some of the planets have managed to hold onto their atmospheres, though the compositions remain tantalizingly unclear. The journey to TRAPPIST-1 would dwarf previous interstellar missions in both distance and complexity. At 40 light-years away, even spacecraft traveling at 20% light speed would require 200 years to complete the voyage. This timeframe necessitates true generation ships, massive vessels capable of sustaining human civilizations for 2 centuries while crossing the void between stars. However, the presence of 7 potentially habitable worlds makes TRAPPIST-1 perhaps the ultimate prize for interstellar colonization. Rather than establishing a single settlement, human colonists could spread across multiple planets, each adapted for different purposes and environmental conditions. Ocean worlds could support aquaculture and marine research, while ice-covered planets could provide freshwater reserves and mining operations for rare minerals concentrated in their frozen crusts. The system's compact nature would also enable unprecedented levels of interplanetary commerce and communication. Travel times between planets would be measured in days or weeks rather than months or years, allowing the development of a truly integrated multi-world civilization. Raw materials mined from one planet could be processed on another and shipped to a third for final assembly, creating an interstellar economy that spans multiple worlds. Beyond these nearest targets lies a world that might be the most Earth-like planet ever discovered. Kepler 452 billion reals, located 1,400 light-years away in the constellation Cygnus, orbits a sun-like star in a 385-day year that closely mirrors Earth's orbital period. This planet receives only slightly more energy than Earth, suggesting surface temperatures that could support liquid water, oceans and climates remarkably similar to our home world. The planet's star, Kepler 452, is 1.5 billion years older than our Sun and 20% brighter, providing a glimpse of what Earth's future might look like as our own star ages and brightens over cosmic time. Despite this increased luminosity, computer models suggest Kepler 452 billion reals could still maintain habitable conditions through cloud formation and atmospheric regulation that prevents runaway greenhouse heating. At 60% larger than Earth, Kepler 452 billion reals likely possesses stronger gravity and a thicker atmosphere that could provide enhanced protection from cosmic radiation and meteorite impacts. The planet's size places it at the upper boundary between rocky super-Earths and smaller gas giants, suggesting it might possess the ideal combination of solid surface area and atmospheric retention to support complex ecosystems. The age of the Kepler 452 system, at 6 billion years old, provides ample time for life to have evolved to extraordinary complexity. If life developed on Kepler 452 billion reals at rates similar to Earth, any organisms there would have had 1.5 billion additional years to evolve beyond anything we can imagine. The planet could potentially host intelligent civilizations that have already achieved interstellar travel, making it both a destination and a potential source of contact with alien intelligence. Yet the enormous distance to Kepler 452 billion reals places it beyond the reach of any conceivable near-term human missions. Even traveling at the speed of light, the journey would take 1,400 years each way, making it accessible only to the most advanced propulsion technologies that remain purely theoretical. Breakthrough concepts like Alcubierre warp drives or traversable wormholes would be necessary to make Kepler 452 billion reals a realistic target for human exploration. The planet represents the ultimate long-term goal for human expansion, a world so similar to Earth that colonists might feel immediately at home under alien skies. Standing on Kepler 452b's surface, would offer the familiar experience of 24-hour days, seasonal changes, and weather patterns that echo Earth's climate zones, but enhanced by the planet's larger size and older, more stable stellar environment. The search for humanity's future home takes us beyond individual planets to consider the fundamental requirements for interstellar colonization. Distance alone doesn't determine accessibility. The type of star, planetary composition, and atmospheric retention all play crucial roles in determining which worlds could actually sustain human life for generations. Red dwarf stars dominate our galaxy, comprising lighthouses burned so efficiently they'll continue roughly 75% of all stellar objects, these cosmic shining long after our sun becomes a red giant and dies. For civilizations planning to survive on geological timescales, red dwarf systems offer unprecedented stability. A colony established around a red dwarf todaying the death of every sun-like star in the galaxy, but could theoretically persist for trillions of years, out till this longevity comes with a deadly price. Red dwarfs are notorious for their violent youth, unleashing stellar flares that can strip planetary atmospheres and sterilize surface environments with lethal radiation. Young red dwarfs fire off superflares containing thousands of times more energy than anything our sun produces, bombarding nearby planets with X-rays intense enough to split water molecules and gradually erode protective magnetic fields. The habitable zones around red dwarfs lie dangerously close to these stellar time bombs. Planets must orbit within a few million miles of their stars to receive enough warmth for liquid water, placing them directly in the path of these radiation storms. Over millions of years, this stellar violence could transform potentially habitable worlds into barren, airless rocks that more closely resemble Mercury than Earth. However, some red dwarf planets might have evolved sophisticated defenses against stellar radiation. Thick atmospheres rich in hydrogen or helium could absorb and scatter harmful radiation before it reaches the surface. Strong planetary magnetic fields, generated by rapid rotation or large molten cores, could deflect charged particles away from the atmosphere entirely. Ocean worlds might use their vast water reserves as radiation shielding, protecting subsurface environments where life could flourish beneath miles of liquid protection. The question of atmospheric retention becomes critical when evaluating habitability around red dwarfs. Unlike Earth, which gradually loses atmospheric gases to space over billions of years, planets orbiting active red dwarfs face accelerated atmospheric erosion from stellar wind and radiation pressure. A world might begin its existence with a thick, protective atmosphere, only to see it stripped away over geological time, leaving behind a desiccated wasteland. Recent observations have detected possible atmospheric signatures around several red dwarf planets, suggesting that some worlds have successfully retained their gaseous envelopes despite stellar bombardment. The presence of water vapor, carbon dioxide, or methane in these atmospheres would indicate not just atmospheric retention, but potentially active geological processes that continue to replenish gases lost to space. Beyond the red dwarf systems lies a category of stars that might offer the perfect balance between longevity and habitability. K-type stars, slightly smaller and cooler than our Sun, burn their fuel more slowly, while avoiding the violent flare activity that plagues red dwarfs. These orange dwarfs could shine steadily for 15 to 45 billion years, providing stable energy sources for planetary evolution without the deadly radiation storms that threaten red dwarf worlds. The habitable zones around K-type stars extend far enough from the central star to avoid the most intense stellar radiation, while remaining close enough to receive adequate heating. Planets in these systems would experience longer orbital periods than red dwarf worlds, potentially supporting seasonal cycles and climate variations that could drive evolutionary adaptation and ecosystem diversity. Alpha Centauri A, part of the nearest star system to Earth, represents an ideal K-type star for potential habitability. Though no confirmed planets have been detected in its habitable zone, ongoing surveys continue searching for Earth-sized worlds that might exist in this cosmic neighborhood. The discovery of a habitable planet around Alpha Centauri A would provide humanity with a nearby target that combines accessibility with optimal stellar conditions for long-term civilization. The composition of potentially habitable planets presents another crucial factor in determining colonization feasibility. Rocky worlds similar to Earth offer solid surfaces for construction and agriculture, along with the geological processes necessary to maintain atmospheric chemistry over long periods. However, these terrestrial planets often possess thin atmospheres that provide limited protection from cosmic radiation and meteorite impacts. Ocean worlds represent a different category entirely, with water-dominated surfaces that could support vast marine ecosystems while providing natural radiation shielding. These aquatic planets might harbour more total biomass than Earth, despite lacking significant land areas. Floating cities and underwater habitats could provide human settlements with access to abundant water resources while taking advantage of the ocean's thermal stability to moderate climate extremes. The recently discovered ocean worlds in our own solar system, including Europa, Enceladus, and Titan, provide templates for understanding how life might develop in aquatic environments. These icy moons harbour liquid water oceans beneath frozen crusts, demonstrating that habitable conditions can exist far from traditional habitable zones. Similar ocean worlds around other stars might offer refuge for life in stellar systems where surface conditions appear hostile. Super-Earths introduce unique challenges and opportunities for human colonization. These massive rocky planets possess gravitational fields strong enough to retain thick atmospheres over geological timescales, potentially providing robust protection from cosmic hazards. However, the increased gravity would dramatically affect human physiology, requiring significant adaptation or technological augmentation for long-term habitation. The atmospheric pressure on super-Earths could be several times greater than Earth's, creating environments where the air itself provides substantial radiation shielding. This dense atmosphere might also enable more efficient heat distribution, moderating temperature extremes between day and night sides of tidally locked worlds. However, the same atmospheric density that provides protection could also create crushing surface pressures that would require specialized habitats and equipment for human survival. Recent studies suggest that super-Earths might be more geologically active than smaller rocky planets, with plate tectonics and volcanism that continues for billions of years longer than Earth-sized worlds. This geological activity could maintain atmospheric chemistry through volcanic outgassing while providing access to mineral resources concentrated by ongoing tectonic processes. The presence of moons around potentially habitable exoplanets adds another layer of complexity to interstellar colonization planning. Large moons could provide additional habitable environments, raw material sources, and gravitational stability that prevents chaotic orbital evolution. The Earth-Moon system demonstrates how large satellites can stabilize planetary rotation and drive tidal processes that may have been crucial for the development of complex life. Exomoons around super-Earths in habitable zones could offer more Earth-like gravity conditions while benefiting from the atmospheric protection provided by their massive parent planets. These satellite worlds might experience complex tidal heating from their planet's gravity, potentially maintaining liquid water even when orbital mechanics would otherwise freeze their surfaces. The detection of exomoons remains at the cutting edge of current astronomical capabilities, but future space telescopes should be able to identify large satellites around nearby exoplanets. The discovery of habitable exomoons would dramatically expand the number of potentially colonizable worlds, turning single-planet systems into multi-world opportunities for human expansion. Binary star systems present both opportunities and challenges for exoplanet habitability. Nearly half of all Sun-like stars exist in multiple star systems, where two or more stars orbit around their common center of mass. Planets in these systems can orbit close to one star in a circumbinary configuration, or they can orbit both stars in a circumstellar pattern. Circumbinary planets, which orbit both stars simultaneously, could experience unique seasonal cycles, as their complex orbital mechanics carry them closer to and farther from the binary pair. These worlds might support exotic climate patterns driven by the varying gravitational influences of two stellar heat sources, potentially creating environments that change dramatically over orbital timescales measured in years or decades. The Alpha Centauri system, with its binary pair of Sun-like stars, represents our closest example of how planets might exist in multiple star environments. Computer simulations suggest that stable planetary orbits could exist around either individual star or in wider orbits that encompass both stellar components. The gravitational complexity of such systems could drive long-term climate variations that accelerate evolutionary processes and create more diverse planetary environments. However, the same gravitational complexity that creates interesting climate dynamics could also destabilize planetary orbits over geological timescales. Planets in binary systems face ongoing perturbations from multiple gravitational sources, potentially leading to orbital decay, ejection from the system, or collisions with their host stars. The challenge of reaching these distant worlds pushes the boundaries of current propulsion technology and mission planning. Even the nearest potentially habitable exoplanets lie thousands of times farther than the most distant human-made objects in our solar system. Voyager 1, humanity's most distant spacecraft, has traveled for over 4 decades to reach the edge of our solar system's influence, yet it would require tens of thousands of additional years to reach even the closest exoplanet. Breakthrough propulsion concepts offer theoretical pathways to dramatically reduce interstellar travel times, but they remain far beyond current technological capabilities. Fusion rockets could potentially achieve velocities of 10 to 15% light speed, reducing journey times to nearby stars from tens of thousands of years to mere decades. However, the engineering challenges of containing fusion reactions in spacecraft and managing the enormous energies involved remain formidable obstacles. Antimatter propulsion represents the ultimate expression of rocket technology, capable of converting matter directly into energy with perfect efficiency. Theoretical antimatter rockets could achieve velocities approaching 30 to 40% light speed, making interstellar voyages possible within single human lifetimes. However, current antimatter production capabilities measure in individual atoms per year, falling impossibly short of the kilograms required for interstellar missions. More exotic propulsion concepts venture into the realm of manipulating space-time itself, rather than simply pushing spacecraft through existing space. Alcubierre warp drives would theoretically compress space in front of a spacecraft while expanding it behind, allowing faster-than-light effective velocities without violating relativity. These concepts remain purely theoretical, requiring forms of exotic matter with negative energy density that may not exist in nature. The development of interstellar propulsion technology represents perhaps the greatest engineering challenge humanity has ever contemplated. Success would require advances in fundamental physics, materials science, and energy production that dwarf the technological leaps that enabled the Apollo moon landings or the development of nuclear weapons. Yet the potential rewards justify even the most ambitious technological development programs. The establishment of human colonies around other stars would ensure species survival against existential threats that could eliminate Earth-based civilization. Asteroid impacts, supervolcanic eruptions, or other cosmic catastrophes could wipe out terrestrial life while leaving interstellar colonies intact to continue human culture and knowledge. The psychological and cultural implications of interstellar colonization extend far beyond mere survival considerations. The establishment of permanent human settlements around other stars would represent the greatest expansion of human experience since our ancestors first left Africa to populate the globe. New worlds would offer opportunities for cultural experimentation, scientific discovery, and artistic expression that could rejuvenate human civilization in ways impossible within our solar system. The choice of which exoplanet to target for humanity's first interstellar colony will ultimately depend on a complex calculation involving distance, habitability, and technological capabilities available at the time of departure. The nearest worlds offer the advantage of shorter journey times and easier communication with Earth, while more distant but potentially superior planets might justify longer voyages for colonists willing to completely sever ties with their home world. As our understanding of exoplanet atmospheres, compositions, and potential for life continues to advance, the target list for human interstellar missions will undoubtedly evolve. Worlds that appear promising today might be ruled out by future observations, while new discoveries could reveal previously unknown opportunities for human expansion among the stars. The selection process for humanity's first interstellar destination involves more than just finding worlds with liquid water and moderate temperatures. We must consider the long-term sustainability of human civilization across cosmic timescales, evaluating factors that won't become apparent until centuries after initial colonization attempts begin. The success or failure of our first interstellar colonies could determine whether humanity becomes a true spacefaring species or remains forever confined to our single solar system. Stellar metallicity emerges as a crucial but often overlooked factor in determining planetary habitability. Stars with higher concentrations of heavy elements tend to form rocky planets with the complex chemistry necessary for technological civilization: iron for tools and construction, silicon for electronics, and rare earth elements for advanced technologies, all depend on stellar systems that formed from gas clouds enriched by previous generations of dying stars. The oldest stars in our galaxy, formed when the universe was young and contained mostly hydrogen and helium, lack the heavy elements necessary for complex planetary chemistry. Even if these ancient stellar systems harbor Earth-sized worlds in their habitable zones, they might be barren ocean worlds, lacking the mineral diversity necessary to support advanced life or human technology. Colonists arriving at such worlds would find themselves on planets beautiful but sterile, unable to develop the industrial base necessary for long-term civilization. Conversely, younger stellar systems formed from gas clouds enriched by supernova explosions possess the full periodic table of elements necessary for complex chemistry and technological development. These metal-rich stars are more likely to host rocky planets with diverse mineral compositions that could support both native ecosystems and human industrial activities for millions of years. The age of potential target stars creates a delicate balance between stellar stability and planetary development time. Stars much younger than our Sun might still be experiencing the violent adolescent phase that could strip planetary atmospheres through intense stellar winds and frequent superflares. The habitable zones around these young stars would be cosmic shooting galleries, where any developing atmospheres face constant erosion from stellar activity. However, stars significantly older than our Sun might have already entered the later stages of stellar evolution that could doom their planetary systems. As stars age and brighten, their habitable zones migrate outward, potentially leaving previously temperate worlds to bake under increased stellar radiation. The most ancient sun-like stars in our galaxy might have already begun the expansion phase that will eventually transform them into red giants, spelling certain doom for any inner planets. The optimal target stars for human colonization likely fall within a narrow age range, old enough to have settled into stable main sequence burning, but young enough to provide billions of years of additional stable energy output. These middle-aged stars offer the perfect combination of current habitability and long-term stability that could sustain human civilization across geological timescales. galactic location plays an equally important role in determining the long-term viability of interstellar colonies. Stars in the galaxy's spiral arms experience higher rates of supernova explosions and gamma-ray bursts that could periodically sterilize nearby planetary systems with lethal radiation. The intense stellar formation activity in spiral arms creates spectacular cosmic nurseries, but also deadly radiation environments that could make long-term habitability impossible. The galactic habitable zone, sometimes called the Goldilocks zone of the Milky Way, encompasses regions with optimal combinations of heavy element abundance and radiation safety. This cosmic sweet spot lies in the galaxy's disk, but between the major spiral arms, providing access to the elements necessary for complex chemistry while avoiding the most intense radiation sources. Our solar system currently resides in this galactic habitable zone, orbiting in the relatively calm space between the Perseus and Sagittarius spiral arms. The nearest potentially habitable exoplanets mostly share this favorable galactic location, suggesting that our initial interstellar colonization efforts will target worlds in similar cosmic neighborhoods with comparable radiation environments. The discovery of atmospheric biosignatures on potentially habitable exoplanets could dramatically influence target selection for human colonization missions. Worlds already harboring life present both extraordinary opportunities and unprecedented ethical dilemmas for human expansion. The presence of existing ecosystems could provide ready-made biospheres that human colonists could integrate with rather than terraform from scratch. However, the detection of alien life would also raise profound questions about humanity's right to colonize inhabited worlds. Even microbial ecosystems represent billions of years of evolutionary development that could be irreversibly altered by human industrial activity. The presence of complex life forms or potential intelligence would make colonization ethically untenable under any conceivable moral framework. Recent advances in atmospheric analysis using space telescopes have begun the systematic search for biosignatures in the atmospheres of nearby potentially habitable planets. The detection of oxygen, methane, or other gases that indicate biological activity could reveal which worlds already host life and which remain available for human colonization without ethical complications. The James Webb Space Telescope and future ground-based extremely large telescopes will be capable of detecting atmospheric biosignatures around dozens of nearby exoplanets within the next 2 decades. These observations will create the first comprehensive survey of life in our cosmic neighborhood, potentially revealing that biology is either incredibly common or extraordinarily rare among nearby stellar systems. The timeline for interstellar colonization depends not just on propulsion technology development, but also on the social and economic factors that would motivate such expensive and dangerous ventures. The cost of mounting interstellar missions would dwarf any previous human endeavor, requiring international cooperation and resource allocation on scales that have never been achieved in human history. Current estimates suggest that even the most modest interstellar probe missions would cost hundreds of billions of dollars, while crewed colonization missions could require economic investments comparable to entire national gross domestic products. The development of interstellar colonization capabilities would necessitate fundamental changes in human civilization's priorities and resource allocation strategies. However, the discovery of imminent existential threats to Earth-based civilization could provide the motivation necessary for such massive investments. Evidence of incoming asteroid impacts, supervolcanic eruptions, or other cosmic catastrophes could galvanize human civilization to prioritize interstellar colonization as a species survival strategy, regardless of cost considerations. The development of self-replicating robotic systems could dramatically reduce the costs and risks associated with interstellar colonization. Automated factory ships could be launched toward target star systems decades or centuries before human colonists, using local resources to construct habitats, infrastructure, and life support systems that would be ready for immediate occupation upon human arrival. These robotic precursor missions could transform raw asteroids and planetary materials into complete colonial infrastructure, including atmospheric processors, agricultural facilities, and manufacturing capabilities. Human colonists would arrive to find ready-made civilizations waiting for them, rather than hostile alien environments that require decades of terraforming and construction work. The concept of digital consciousness transfer offers perhaps the most radical approach to interstellar colonization, potentially allowing human minds to make the journey to distant stars without requiring physical life support systems during the voyage. Advanced brain scanning and simulation technologies could theoretically upload human consciousness patterns into digital substrates that could survive the centuries-long voyages between stars. Upon arrival at target systems, these digital minds could direct robotic systems to construct biological bodies or maintain existence in purely digital environments. This approach would eliminate the massive life support requirements that make generation ships so expensive and complex, while allowing essentially unlimited numbers of human minds to participate in interstellar colonization efforts. However, the philosophical and technical challenges associated with consciousness transfer remain formidable. Questions about the continuity of personal identity, the fidelity of digital consciousness simulation, and the psychological effects of existing in purely digital environments for centuries would need to be resolved before such approaches could be considered viable. The psychological challenges of interstellar colonization extend far beyond the technical difficulties of crossing space between stars. Human colonists would face complete separation from Earth-based civilization, with communication delays measured in years or decades that would make real-time interaction with terrestrial society impossible. The isolation experienced by interstellar colonists would be absolute in ways that no human society has ever experienced. Even the most remote human settlements on Earth maintain some connection to global civilization through communication networks and transportation systems. Interstellar colonists would be truly alone, forced to develop completely self-sufficient societies without any possibility of assistance from their home world. This isolation could drive rapid cultural evolution as colonial societies adapt to their new environments and develop unique social structures, optimized for survival in alien worlds. Within a few generations, interstellar colonies might develop cultures and values systems so different from Earth-based civilization that they would be barely recognizable as human societies. The genetic isolation of small colonial populations also presents significant challenges for long-term species survival. Interstellar missions would likely launch with populations of only a few thousand individuals, creating genetic bottlenecks that could lead to inbreeding depression and reduced evolutionary fitness over multiple generations. Advanced genetic engineering and artificial reproductive technologies could potentially mitigate these population bottleneck effects by maintaining genetic diversity through artificial means. Frozen genetic material from Earth could provide the raw material for introducing new genetic combinations into colonial populations centuries after initial settlement. The development of artificial wombs and genetic modification technologies could also allow colonial populations to adapt themselves to alien environmental conditions over time. Rather than terraforming entire worlds to match Earth conditions, human colonists could modify themselves to thrive in the atmospheric pressures, gravity levels, and radiation environments of their new homes. The question of which world deserves to become humanity's first interstellar colony ultimately depends on a complex optimization problem involving distance, habitability, resource availability, and long-term sustainability. The nearest potentially habitable worlds offer the advantages of shorter journey times and easier communication with Earth, making them ideal targets for initial colonization attempts that could establish proof of concept for interstellar expansion. However, more distant worlds with superior habitability characteristics might justify longer voyages for colonists willing to make permanent commitments to interstellar civilization. These distant paradises could offer environmental conditions so superior to Earth that they would attract the most ambitious and capable colonists, potentially establishing interstellar societies that surpass their terrestrial origins. The selection process will likely involve launching multiple smaller probe missions to nearby potentially habitable worlds before committing to full-scale colonization efforts. These robotic scouts could provide detailed environmental assessments, atmospheric analysis, and resource surveys that would inform final destination selection for human missions. The race to identify and reach humanity's first interstellar destination has already begun, driven by advances in exoplanet detection, propulsion technology development, and growing awareness of existential risks facing Earth-based civilization. Within the next few decades, we will likely identify the specific world that will become humanity's first home among the stars, beginning the greatest journey in our species' history. The technological breakthroughs required for reaching these distant worlds may arrive sooner than anyone expects. Private agencies are companies and government revolutionary, already testing interstellar journey propulsion concepts that could slash times from tens of thousands of years to mere decades. Breakthrough Starshot's light sail technology represents just the beginning of what's possible when human ingenuity meets the challenge of crossing interstellar space. Solar sail technology has evolved far beyond simple reflective surfaces pushed by starlight. Advanced concepts involve ultra-thin metamaterials, engineered at the molecular level to achieve unprecedented strength-to-weight ratios. These gossamer spacecraft, weighing just grams but spanning kilometers, could be accelerated to 20% light speed by powerful ground-based laser arrays. The engineering challenges are staggering, but the physics remains sound. Imagine thousands of tiny spacecraft, each no larger than a smartphone, racing toward Proxima Centauri at velocities that would carry them past Earth's moon in just 2 hours. These nanoprobes would carry miniaturized cameras, spectrometers, and communication systems capable of beaming back humanity's first close-up images of an alien world. The data they collect could reveal whether Proxima b harbors the atmospheric conditions necessary for human colonization. But light sails represent only the first generation of breakthrough propulsion technology. Fusion rockets, still in early development stages, promise to deliver massive payloads to nearby star systems within human chemical rockets that exer lifetimes. Unlike minutes, fusion drive suss their fuel in could operate continuously for years, gradually accelerating massive colony ships to significant fractions of light speed. The fusion fuel exists in virtually unlimited quantities throughout the cosmos. Every star system contains vast reserves of hydrogen and helium waiting to be harvested by interstellar travelers. Colony ships, equipped with magnetic scoops, could refuel during flight, collecting interstellar gas to extend their range indefinitely. This capability would transform interstellar travel from one-way suicide missions into sustainable transportation networks linking multiple star systems. Recent breakthroughs in magnetic confinement and laser-triggered fusion have brought these concepts closer to reality. Private fusion companies claim they'll achieve sustained fusion reactions within the next decade, potentially providing the power sources necessary for interstellar propulsion systems. The same technology that could provide clean energy on Earth might also provide the keys to the stars. Even more exotic propulsion concepts venture into the realm of manipulating space and time themselves. The Alcubierre warp drive remains purely theoretical, but recent mathematical refinements have reduced the exotic matter requirements from planet-sized quantities to merely spacecraft-sized amounts. While still beyond current capabilities, these calculations suggest that faster-than-light travel might not violate the fundamental laws of physics. Wormhole travel represents the ultimate expression of space-time manipulation, potentially allowing instantaneous travel between distant points in the universe. Naturally occurring wormholes, if they exist, might provide cosmic highways between star systems, reducing interstellar journeys from centuries to minutes. The search for these space-time tunnels has become a legitimate area of astrophysical research, with scientists scanning the cosmos for gravitational signatures that might indicate traversable wormholes. The detection of artificial megastructures around distant stars could reveal that other civilizations have already solved the interstellar transportation problem. Dyson spheres, ring worlds, and other massive engineering projects would be visible to our telescopes as artificial alterations to stellar brightness patterns. The discovery of such structures would prove that intelligent life can achieve truly cosmic-scale engineering capabilities. But even with revolutionary propulsion technology, the challenges of sustaining human life during interstellar voyages remain formidable. Generation ships designed to support human populations for centuries would need to function as completely self-contained ecosystems, recycling air, water, and organic matter with perfect efficiency. Any failure in these closed-loop life support systems could doom entire colonial expeditions. The psychological challenges of multi-generational space travel present equally daunting obstacles. Children born during interstellar voyages would grow up knowing they would never see their destination, living their entire lives in artificial environments while traveling toward worlds they could never visit. These intermediate generations would need to maintain the colonial mission's purpose across decades of monotonous space travel. Advanced hibernation technology could potentially solve both the life support and psychological challenges of interstellar travel. If human metabolism could be slowed to near-death states for decades at a time, colony ships could carry much larger populations while requiring minimal resources during the journey. Colonists would essentially sleep their way to the stars, awakening only upon arrival at their destination. Recent research into induced hibernation has shown promising results with small mammals, successfully placing animals in suspended animation for weeks at a time without apparent long-term health effects. Scaling these techniques to humans and extending hibernation periods to years or decades represents a significant challenge, but one that appears technically achievable within the next few decades. The development of artificial intelligence sophisticated enough to manage complex spacecraft systems during multi-decade voyages could eliminate the need for conscious human oversight during interstellar travel. AI systems could monitor life support, navigation, and communication functions while human crews remain in hibernation, awakening the colonists only when their active intervention becomes necessary. These AI guardians would need to operate independently for longer periods than any human-made system has ever functioned, making critical decisions about course corrections, system repairs, and emergency responses without human input. The reliability requirements for such systems exceed anything ever attempted in human technology, demanding unprecedented levels of redundancy and self-repair capability. The arrival at destination star systems would present colonists with challenges that dwarf the difficulties of interstellar travel itself. Even the most promising exoplanets would likely require extensive terraforming before they could support human civilization. Atmospheric processes, weather modification systems, and ecological engineering projects could take centuries to transform alien worlds into human habitable environments. The terraform process would begin decades before human colonists arrive, carried out by robotic systems launched on faster trajectories than the main colony ships. These automated terraforming platforms could begin atmospheric modification, soil preparation, and infrastructure construction, while human colonists remain in hibernation during their slower journey to the destination system. Atmospheric engineering on planetary scales would require manipulating entire atmospheric compositions, potentially adding or removing trillions of tons of gases to achieve breathable conditions. Carbon dioxide scrubbers, oxygen generators, and ozone layer construction would need to operate continuously for decades before human-safe atmospheric conditions could be established. The introduction of Earth-based ecosystems to alien worlds presents unprecedented ecological challenges. Terrestrial plants and animals would need to adapt to different gravity levels, atmospheric pressures, and radiation environments, while establishing sustainable food webs in completely alien soil compositions. The failure of key species to adapt could collapse entire planned ecosystems, leaving colonists without sustainable food sources. Genetic modification of both colonists and Earth species could provide solutions to these adaptation challenges. Enhanced humans with improved radiation resistance, modified bone density for different gravity levels, and altered metabolisms for non-terrestrial atmospheric compositions could thrive in environments that would kill unmodified humans within hours. The ethical implications of creating genetically modified human subspecies specifically adapted for life on alien worlds raise profound questions about the future of human identity. Within a few generations, the descendants of Earth-based humans might diverge so significantly that they could no longer be considered the same species as their terrestrial ancestors. Multiple human subspecies adapted for different planetary environments could eventually populate dozens of star systems, each developing unique cultural and biological characteristics shaped by their alien homeworlds. These divergent human populations might eventually encounter each other as interstellar travel becomes routine, creating unprecedented scenarios of contact between related but distinct intelligent species. The establishment of communication networks linking Earth with interstellar colonies would create the first truly galactic human civilization. Quantum entanglement communication, if it proves technically feasible, could provide instantaneous information exchange across any distance, maintaining cultural and scientific connections between worlds separated by dozens of light years. Without faster-than-light communication, interstellar colonies would remain isolated for decades or centuries between message exchanges. Scientific discoveries, cultural developments, and technological innovations would evolve independently on each world, creating a diversity of human civilization that could exceed anything achieved during terrestrial history. The economic implications of interstellar colonization would fundamentally transform human civilization even before the first colony ships launch. The resource requirements for mounting interstellar missions would necessitate unprecedented levels of international cooperation and resource pooling. National boundaries would become meaningless when facing challenges that require the combined efforts of the entire human species. The development of asteroid mining, space-based manufacturing, and orbital construction capabilities would provide the industrial infrastructure necessary for building interstellar colony ships. These space-based industries would themselves transform human civilization, providing access to resources and manufacturing capabilities that dwarf anything possible on Earth's surface. The psychological impact of knowing that human civilization extends beyond Earth would alter fundamental aspects of human culture and philosophy. Religious and philosophical systems would need to accommodate the reality of multiple human worlds, each potentially developing unique approaches to meaning, purpose, and spiritual understanding. The first images transmitted back from successful interstellar colonies would mark a turning point in human consciousness, comparable to the first photographs of Earth from space. Seeing human cities thriving under alien stars would prove that our species possesses the capability to survive and flourish anywhere in the universe where physical laws permit life to exist. Children born on these distant worlds would be the first truly extraterrestrial humans, native to alien planets with no direct connection to Earth beyond their genetic heritage. These cosmic natives would view Earth as an ancestral homeland rather than home, potentially developing cultural perspectives that previous generations of humans could never imagine. The success of humanity's first interstellar colonies would establish proof of concept for unlimited expansion throughout the galaxy. Once the basic techniques for interstellar travel and planetary colonization are perfected, nothing would prevent human civilization from spreading to every habitable world within our cosmic neighborhood, and eventually beyond. The transformation from a single-planet species to a multi-world civilization would represent the greatest transition in human history, comparable to the development of agriculture, the Industrial Revolution, and the Information Age combined. Within a few centuries, humanity could evolve from struggling to survive on one world to thriving across dozens of star systems scattered throughout the galaxy. The choice of which exoplanet becomes humanity's first interstellar destination will ultimately determine the trajectory of this cosmic expansion. A successful first colony would validate the technologies and strategies needed for subsequent missions, while failure could set back interstellar colonization efforts by decades or centuries. The stakes could not be higher. The next few decades will determine whether humanity remains forever confined to our solar system or begins the greatest journey in our species' existence. The most habitable exoplanets are waiting in the darkness between stars, ready to become humanity's new homes among the cosmic wilderness. These worlds represent more than just backup planets for human survival. They offer the possibility of human cultures, sciences, and arts developing in ways impossible within our solar system's constraints. Each new world would become a unique experiment in human civilization, potentially producing insights, technologies, and cultural innovations that could benefit all of humanity across multiple star systems. The race to reach the stars has already begun. The question is not whether we will succeed, but how quickly we can transform from cosmic prisoners to galactic citizens. The most habitable exoplanets we could reach next are calling to us across the interstellar void, promising futures we can barely imagine for the children who will inherit the galaxy. The transformation awaiting humanity extends beyond mere survival to encompass a complete reimagining of what it means to be human in a cosmic context. Standing on the surface of these distant worlds, our descendants would witness sunrises painted in colors that have never graced Earth's sky. Binary star systems would cast double shadows across alien landscapes, while planets with rings would display celestial architecture that dwarfs Saturn's modest bands. The atmospheric conditions on super-Earths would create weather phenomena impossible on our home world. Storm systems powered by 3 times Earth's gravity could generate winds that reshape continents within decades. Lightning strikes in dense hydrogen atmospheres might produce electrical displays visible from orbit, turning entire planets into cosmic beacons that pulse with natural energy. Ocean worlds would offer underwater civilizations that could span entire planetary surfaces. Cities built in the crushing depths would harness geothermal energy from underwater volcanic systems, creating self-sustaining communities that never see starlight. These aquatic metropolises could support populations in the millions, while maintaining perfect ecological balance with alien marine ecosystems. The mineral wealth of these distant worlds would revolutionize human technology in ways we can barely comprehend. Planets formed around metal-rich stars could contain ore deposits with concentrations of rare elements that exceed anything found on Earth by factors of thousands. Mining operations on these treasure worlds could provide raw materials for technologies that seem like magic from our current perspective. Gravity variations across different exoplanets would drive the development of human subspecies adapted for specific environmental conditions. Low-gravity worlds would produce humans with elongated limbs and enhanced cardiovascular systems, while high-gravity planets would create compact, incredibly strong populations with bones dense as stone. These physical adaptations would occur naturally over generations, creating human variants perfectly suited for their chosen worlds. The psychological evolution of interstellar humans might prove even more dramatic than their physical changes. Minds that develop under alien skies, surrounded by landscapes that bear no resemblance to terrestrial environments, would think in patterns fundamentally different from Earth-based cognition. These cosmic natives might solve problems and perceive reality in ways that Earth humans could never achieve. Communication between worlds would create the first truly galactic internet, linking human consciousness across distances that dwarf our current global networks. Ideas, discoveries, and cultural innovations would flow between star systems, creating a collective human intelligence that spans multiple worlds. This galactic brain could solve problems that individual planetary civilizations could never tackle alone. The energy resources available in other star systems could power technologies beyond our wildest imagination. Dyson sphere construction around red dwarf stars could provide energy outputs equivalent to billions of fusion reactors, enabling planetary engineering projects that reshape entire worlds within decades. These cosmic power sources could support populations in the trillions while maintaining living standards that would seem utopian from our current perspective. The discovery of alien life on these worlds would present humanity with the greatest philosophical challenge in our species' history. Encountering ecosystems that evolved independently from Earth would prove that life represents a universal principle rather than a cosmic accident. These alien biospheres could teach us new approaches to medicine, engineering, and environmental management that revolutionize human civilization. The greatest journey in human history has already begun. From Proxima Centauri's twilight zones to TRAPPIST-1's gravitational symphony, from Tau Ceti's asteroid treasure troves to Kepler 452b's ancient skies, we've mapped the stepping stones that could carry our species beyond the boundaries of home. These aren't just distant worlds floating in cosmic darkness. They're humanity's future addresses, waiting for us to develop the courage and technology to claim them. The children born today might live to see the first images beamed back from these alien shores, proving that Earth was never meant to be our final destination, but rather our launching pad to the galaxy itself.